here. Okay. So for today, we're just going to look at section 1D and with the title Analyzing Arguments. Okay. All right. So this is what is an argument. So, an argument uses a set of premises. Right. So this sets up, premises is you got the prefix pre, so this sets up the foundation of what you are arguing, and this set of premises will support one or more conclusions. Okay. So working definition here for what an argument is. A set of premises to support one or more conclusions. Now, there are sorry about this. 1 second. All right, two types of arguments. We've got ourselves inductive and deductive. Okay. Now, just as a kind of a way to remember how each functions, a inductive moves from specific premises. So it moves from specific premises to a general conclusion. A deductive argument has general premises and moves to a specific conclusion. Okay, so another way that I like to try to think about differentiating between the two types of arguments. In an inductive argument, I list out a series of examples, and from those examples, I draw a conclusion. All right, so it has rained for the last 4 days. Therefore, tomorrow it's going to rain. Now, would my conclusion absolutely be true? No. All right. So, and that's the thing about inductive arguments. There's no way to conclusively prove your conclusion true. What we can say is that we judge the validity of the argument on its strength. And that is looking at those examples and then drawing a conclusion. Right? So, in a deductive argument, a rule is stated. And then from that rule, we make a specific conclusion. But, and so if the rule is true, and it logically follows from our premises that we can get to the conclusion, then we can conclude absolutely that it is true. So in mathematical proofs, if I'm trying to prove a theorem, which is the basis of all mathematics, when we look at a mathematical system, we write what are called conditional statements. If we assume this, then we can conclude this, and then we write a deductive argument. So inductive arguments cannot be used to actually prove mathematical theorems. It has to be a deductive type argument. All right, so turn the page. And again, anytime you want to see a previous page, I can always turn back. So I'm going to turn the page. Evaluating. That is a L. Now. Inductive arguments. Right. So again, an inductive argument cannot prove its conclusions true. Right. So inductive argument cannot prove its conclusions true. So is evaluated in terms of its strength. So if the argument is strong and it makes a compelling case for a conclusion, it's weak if the conclusion is not well supported by the premises. Right. So, but that is just basically, we always evaluate inductive arguments in terms of its strength. Example of a inductive argument. And so I'm not going to write all this down. Just going to verbally spit it out. So here's some premises. All right. Birds fly into the air, but eventually come back down. People who jump into the air fall back down. Rocks thrown into the air come back down. Balls thrown into the air come back down. So those were 4 premises listed out. Conclusion: what must go up, what goes up must come back down. Now, is that true? That is, when you hear me say what goes up must come down, is that conclusion true? Can you think of anything that goes up and does not come back down?
Balloons.
Balloons. All right. Now that definitely filled with helium, right? I may say eventually that helium in the balloon will dissipate and the balloon will come back down eventually. It can't leave Earth's atmosphere altogether, but that is definitely thinking. So already we got an issue with the conclusion. I was thinking more along the lines of rockets. When we launch a satellite, if it gains enough speed, it will leave the Earth. So and to not come back down. But so there's 2 examples right there. Would I consider, though, the argument to be, I would say it's moderately strong. I listed out 4 premises, all which were true. But again, the conclusion itself is not true. But again, when I read out the argument, again, I listed out a set of specific premises. And that's what, so just tuning in on what is an inductive argument, that's what I'm keying on, is just some specific premises, and I make this general conclusion from there. All right. A deductive argument, example of all politicians are married. Senator Harris is a politician. My conclusion: Senator Harris is married. Okay. Now, in terms of what I would say here is, in evaluating that argument, now it is deductive in the sense that I just state a rule, very general rule. 2 premises: all politicians are married, and Senator Harris is a what? Politician. And to make a specific conclusion from those general premises that Senator Harris is married. Now, so evaluating that second one, evaluating a deductive argument. That's all right. So, 2 criteria for evaluating the deductive argument. So validity and then soundness. So, and then they come in order. So you first evaluate its validity. And the argument is valid if its conclusions follows necessarily from its premises. put a 1 here, from its premises. Two, argument is sound if it is valid, right? So, so the argument's sound. First off, if it's not valid, it's not sound. So you first have to check the validity. That is, that its conclusion necessarily follows necessarily from its premises. So it's sound if it is valid, and its premises are all true. Okay. So you need those both things to be sound. You have to be valid, and that is that the conclusions do follow necessarily from its premises. Um, so if you're valid and the premises themselves are true, so it is possible you could have a valid argument. That is, the conclusions follow from the premises, but one of your premises or all of your premises were not true. In which case we'd say, okay, then the argument's not sound because we had a premise. So it can logically connect and be valid, but not be sound because you have a premise that in itself is not true. Okay. Now, all right. So kind of looking at some examples using Venn diagram, which you would have worked on in 1C for homework, using a Venn diagram to check out uh, uh, evaluating a deductive argument. So let's go back to our politician. So we had a premise, two premises. You had a premise, all politicians are married. And Senator Harris is a politician. And then the conclusion, I'm just going to leave it CON, Senator Harris is married. All right. So checking for validity. Using a Venn diagram. So remember, validity is that the conclusion necessarily follows from the premises. All right, so if we use the circle here, and this inside this circle was married people. Okay. And now it says all politicians are married, so we can have a circle inside here, and these are our politicians. So that's a POL in there. Now, if we let X be for Senator Harris, well, what we need to have happen is the X needs to be in that most inner circle, but he is a what? Politician. So he would go inside here, which is inside that the married people. So now, so again, that once I place that X in that inner circle, if I can't place the X in the inner circle, that variable X for Senator Harris, then it's not a valid argument because your conclusion is not necessarily following from the premises, but this is valid. Now, one thing that we would also look at soundness here. So remember, soundness has to be that your argument's valid, which this one is, but all your premises have to be true. And there I would have a problem with this in that one of those premises, specifically all politicians are married, that what is not true. So this would be an example of valid. And again, this argument here with the Venn diagram, by being able to put the X right in here, inside the inner circle shows that it's valid, but not sound for the fact that one of the premises is not true. Okay. So another one. Looking at another argument. So let's say I have a premise, and this premise is all fish live in water. And we got a premise, whales are not fish, and missing an H. Whales are not fish. Okay. Conclusion. Whales do not live in water. All right. So there's our argument. So let's go to draw a Venn diagram here. So I have a circle here. And so inside this set, things that live in water. And one thing that lives in water are fish. All right. All right. So, since we have a premise here that says whales are not fish, has to be outside of here, and we have all fish live in water, that puts the X right there, not in that center circle. So the premises do not necessarily lead us to this conclusion. All right, so there's no way to connect the two. So this argument is not valid. And because it's not valid, then we know we're not sound. So again, you have to have validity first. All right. So there will be some problems in homework where you set up a Venn diagram just like this. And the way they're formatted is multiple choice. You're given like 4 or 5 Venn diagrams, labeled with X, a variable placed in there, and you have to pick the correct one based on the argument at hand. All right, now. Conditional statements. There are 4 types. Now, when I say a conditional statement, it comes in this form. If this, then that. Now, we're going to use P and Q so that structuring it like this. So if P, then Q. Okay, so if P, then Q. All right. Now, this one, the book refers to this as affirming the hypothesis. Okay. Now, this is valid. So, now, next one. If I use this symbol here, which is you can find on your keyboard, is called tilde. So the tilde symbol, one little squiggly line. In logic, it means not. So just the opposite. So if I state well, don't need that one quite yet, but if I reverse these two, if Q, then P, and then this is referred to as affirming the conclusion. All right, so if you assume the conclusion true, if you assume it to be true, that does not necessarily logically go back to show the hypothesis. So P is hypothesis, Q is conclusion. This is an invalid argument. All right, so now I'm going to use the tilde of the not. If I state if not P, then not Q. All right. This is referred to as denying the hypothesis. and this also is invalid. All right, so again, it does not logically connect. So if you assume the hypothesis is not true, that will not necessarily mean that the conclusion is not true. So, but if I switch these two and say, if not Q, then not P, this is referred to as denying the conclusion. That is valid. That does logically connect. If you assume the conclusion is not true, you can show that the premise itself was not true. Those two logically connect. Now, I'm not going to write these down. I'm just going to throw them out there in case you ever hear these terms used. It is not used in the text, this particular textbook. These terms are not used in the homework. But these four statements, you could, in another book, or if you're in another class looking at logic, refer to this first one as my conditional. Then this is referred to the second statement. So kind of like a little bit more succinct naming system. The second one is the converse. Flip them, convert them, converse. The third one, this one, is the inverse. And one of my favorite words of all time, contrapositive. I just like saying it. I don't know why. Contrapositive, which is the converse of the inverse. So, but conditional and contrapositive are valid arguments. So, and conditional statements. All right. So there will be a few homework problems in which you are given a statement and then have to determine which one of the four it is, which one of these follow four, and then you're asked about validity. So, and again, here is two of them. This one and the last one are valid, and these two are not. So, affirming and denying, affirming the conclusion or denying the hypothesis. All right. Okay. So I think what I'd like to do now is look at a few of the actual homework problems. So there are in section 1D in this next homework assignment, there are going to be, there are 22 total problems. And so I'm looking at problem number 1. And the instructions say on problem number 1, summarize the differences between deductive and inductive arguments, give an example of each type. And so what you're, and this is, I think it's got, looks like about 3 parts here. So the first one, ask you to, which of the following are properties of inductive arguments? And you're given 6 choices, of which 3 are true. Right? That is that they are properties of inductive arguments. So I'm just reading through all the choices here. Choice A, and remember, we're looking for properties of inductive arguments. So remember, we said that that has what specific premises, and we move to a general conclusion. So statement A, it cannot prove its conclusion true. At best, the conclusion is probably true. Yes, that is an inductive argument. A specific conclusion is deduced from a set of more general or equally general premises. So remember, that was for deductive, so that you wouldn't select that. Next, when a conclusion is formed by generalizing a set of more specific premises, yes, that's how we defined out inductive reasoning. D, it can be analyzed only in terms of its strength. Yes, that's the only way we can analyze an inductive argument is in terms of its strength. So you would select that one. Now I've selected 3. So as I said, you were going to choose 3 out of the 6. So the other 2 are it can be analyzed in terms of its validity and soundness. If it is valid, it is valid as if its conclusion necessarily follows from its premises. It's sound if it is valid and the premises is all true. Yes, that's what we said about deductive arguments. And the last statement is it is valid. It can be valid even when the conclusion is blatantly false, and that is true. So it may not be sound, but it can be valid. It can, you can have premises which are not true, but it does the argument logically follows from the premises to the conclusion. All right. So then when you do the deductive, you're actually given the same 6 statements, and then of course you're going to pick the other 3. All right. Then you're given which of the following are examples of inductive arguments. So I'm kind of giving you a heads up here. Only one of them is going out, and you're given a choice of 4, and only one of them is actually going to be an inductive argument. And okay, and only one of them is, again, and I will just give you a forewarning on, again, I'm still on number 1. One of them, there are 2 that are clearly deductive. You can eliminate them immediately. And so then you've got 2 that each look like they're inductive arguments, but one of them fails because the conclusion doesn't match up with your examples. So read carefully. So that is that, and then you're given pick out 2 which are deductive. And remember, and they give you the same 4 examples again, and 2 of them, again, are deductive arguments. So, all right, so that is number 1, addressing inductive and deductive. Number 2 deals with deductive arguments solely, and looking at validity and then soundness. Okay. Now, I did not mention this one, and I should have, and I apologize. Number 3 deals with what is called a chain of conditionals. Okay. So, if you have a chain of conditionals, looks like this. And you get a chain linking up 3 or more premises. So, or 3 or more conditionals. So you could have minimum 2 premises. So it does something like this. If P, then Q, and then the next premise is going to go if Q. So notice that is this same one here, and I apologize. I need to be a little more consistent. If Q, then R. So it's chaining simply because the conclusion here is the same as the hypothesis here. And then your conclusion would go from if P, then R. So you could have more conditionals. In this case, we have 3, P, Q, and R. Okay. All right. So number 3 deals with just idea of a chain of conditionals. And so the very first part of the problem just has you spell out, what is a chain of conditionals. And again, it is a chain of 3 or more conditionals. So, and it is a deductive argument. So I should have also said that. It's always going to be looking at deductive. So chain of conditionals is a type of deductive argument that involves a chain of 3 or more conditionals. And then you just have to pick out of a choice of 4, what is it, connects the chain, and it's this. So basically it gives you 3 other selections where these do not match up. All right. Number 4, just ask the question, can inductive logic be used to prove a mathematical theorem? And we already said no, it has to be a deductive argument. All right, so inductive logic cannot be used there. All right, 6 just deals more with deductive and validity. Number 6, looking at an argument, and then we're going to have several more like this. Looking at an argument and discussing whether it is deductive or inductive. Right? So the specific argument on number 6 is, I have never found mail in my mailbox on a Friday. The postal service must not have Friday deliveries. And so you're given 4 choices. 2 of them are deductive, 2 of them are inductive. So the first thing I would want to try to figure out is it inductive or deductive? And in this case, I have never found mail in my mailbox on a Friday. So that's a premise. Conclusion, the postal service must not have Friday deliveries. The first statement was specific, and then I moved to a general conclusion. That is inductive. And so your 2 choices for then inductive, what they do is they one of them's right, one of them's wrong. Remember that inductive moves from a specific premise to a general conclusion. And so that's the one you want to select. They give you also a choice of inductive, moving premises general, moving specific conclusion, but that's just the opposite of inductive. All right. All right, so I'm going to read it. Just moved to number 7. Every coach must know his sport well. Marty Wright is a baseball coach, so Marty Wright knows baseball well. So then, would you say that is inductive or deductive? So again, look at the premise. Was it a general kind of stating as a rule, or was it a specific example as a premise? And in this case, every coach must know his sport well. That's general. And then I'm moving to that specific conclusion that Marty Wright knows baseball well. So this would be a deductive argument. All right, so 8. Is also same sort of problem. Number 9 Um, we are looking at an inductive argument. It lists out this one. I think I can. So I'm at number 9. Determine the truth of the premises of the following arguments, then assess the strength of the argument, discuss the truth of the conclusion. So I'm going to use P for premise here. And it gives 3 premises. First one is 5 plus 4 is equal to 9. Next premise is 2 plus 7 equals 9. The last one is 4 plus 3 equals 9. Now, conclusion. The sum of an odd integer and an even integer is an odd integer. So, sum of even integer and odd integer is an odd integer. Okay, so you're asked to pick out which premises are true. Well, actually, all 3 of them are true. You got a 4th choice of none of the premises are true, so you wouldn't select that one. And then, so that would be the first part of the question, and then assessing the strength. And you're given on 3 choices on that. On the strength, it was the argument is moderately strong. The conclusion is false. The argument is moderately strong. The conclusion is true. And the last one, the argument is very weak. The conclusion is false. You would choose moderately strong, and the conclusion is what? True. It never actually talks about this being an inductive argument, but that's what it is. So, and it is true that if you take any odd integer and add an even integer to it, you're going to get an answer which is an odd integer. But you would, to actually formally prove that in mathematics, you've got to use a deductive argument. So, again, this would be an example of an inductive argument. All right. 10 does the same thing. And then we move to looking at where I'm going to use a Venn diagram. I've got a deductive argument, and I use a Venn diagram to first show for validity. And then you're asked about its soundness. So remember, to be valid, that the conclusions must necessarily follow from the premises. And then to be sound, it's got to be valid, and all your premises have to be true. So in this particular case, you would first let's turn the page and set up the specific of the problem.
Can you tell me what it says after con before you turn the page? My electricity went off and came back on.
Oh, geez, I'm sorry. Yeah, and again, my handwriting is I'm a little bit better on the chalkboard.
I understand. This is not an easy.
Yeah, what the actual issue is, the piece of technology I am writing on, the tablet. I will have to, just a little sidebar, and then I'll tell you what I wrote there. When we first last March of 20, and all of a sudden we moved into this environment for all classes. I didn't have this piece of technology that I was using, and I had the whiteboard because that's part of Zoom. I had to use my mouse. And
Oh,
it
my.
literally looked like a first grader's. I mean, it was rough. So we all just kind of took our time and laughed about it.
Yeah.
So, but yeah, and then I got this piece of technology and got installed on my computer, and that moved me up to about a 5th grade to 6th grade level. So at least I'm a little bit more legible. So anyway, what this says is sum, SUM, of even, and I wrote INT for integer. Sum of even integer and odd integer is an odd integer.
Okay, thank you.
You're welcome. All right, so, sorry, number 11, we have a deductive argument, and it looks out like this. Premise, all boulders are large. And then we have another premise that says small rock is a boulder. And conclusion, small rock is large. All right, so if we kind of discuss or just construct a Venn diagram, and let X represent small rock. So X will be small rock. Then got the set of large things. And boulders, which by our premise, all boulders are what? Large. So inside there, we'll have another circle and we'll put boulders. All right. Now, where can we place our X? Well, that is, where is our small rock? Small rock is a what? That's premise. Small rock is a boulder. So it's got to be in here. So remember, if that X ends up inside that inner circle, then this argument is what? Valid. That is, our conclusion necessarily follows from our premises. So it is a valid argument. Now, this is where, yeah, I understand the construction of the problem, but it can be a little confusing. So this was part A. It is valid. Would you say that it is sound? So remember, to be sound, it's what? Got to be valid. And so that your conclusion necessarily follows from your premises. But are my premises necessarily, or are they true? Are all boulders large? And that's a little bit ambiguous to start with. So, but there's on this one right here, that particular premise, I can't say that is absolutely true. And so they were trying to get an example which we had valid, but not, this one is not sound. And again, the reason being is it's not sound if you have a premise that's, it's valid. So logically everything flows. But if you have a premise that's not true, then it's not sound. And that is the problem. You have a premise which is not necessarily true. All right. Any questions on that one? All right. So 12 does exactly the same thing. 13 deals with a chain of conditionals. So which we went over. All All right, so 14 deals with a term I have not used. I'm going to turn the page. It's all right. On number 14, deals with the idea of counterexample. Right. And I want to actually rewrite this. This is one word. Right. So great word if you're playing Scrabble. And you can hit the old triple word score. All right, counterexample. All right. So I always say it's much easier to disprove something than to prove it, because to disprove, all I got to, if you have a statement, all I got to do is find one example where it's not true. So, and so what they do here on this particular one is give you a statement and then give you a selection, a bunch of about 8 of them. 7 of them are specific examples, and then the last one that just says there is no counterexample. And then it asks you, is the rule true in and of itself? Now, this particular one is this. It says for all real numbers. For all real numbers, this. Now, this is known as the commutative law of addition. That is what says I can take any 2 real numbers and add them in any order I want. That is 3 plus 5 is the same thing as 5 plus 3. In both cases, you get 8. Addition is actually commutative. Subtraction is not. 3 minus 5 is not the same thing as 5 minus 3. They list out, so they basically give you on each selection a value for A and a value for B, but they're all true. So there are no counterexamples, and then the rule's true. Now, bear in mind, as you work these problems, that's the specific one that is number 14 that I'm looking at. They'll give you when you get to do number 14, it'll probably be another type rule. And there may be some counterexamples in your list, and then you would just easily answer that the rule's not true. All right. And I, specifically, you really should point out here, even if every counterexample they gave you, or every example they gave you was true, does not necessarily mean the rule itself is true. They just didn't list out a counterexample. All right. Actually, no. So down 14, it's true. 15 is the same thing. On number 15, they say for positive real numbers. So, and I'm trying to help you out here in terms of don't get caught on this. So make sure you always read, it says for positive real numbers, square root of A plus B equals square root of A plus square root of B. So I'm going to go ahead and just tell you right now, in general, this is not true. Right? This is not true. You can't split it up and take the square root of each individual thing and get the same result as if you add now you can for some numbers, but not all. So in general, this is not a true rule. And they give you again the list of 8, one of which is there's no counterexample. 4 of them are counterexamples. And then on the other 3, one of them actually is true. That is, if you let A be 0 and B be 0, that rule works. But then they give you, in one case, A is 2 and B is negative 2, which doesn't work here. The issue is, however, remember what it said was this was only applying for what? Positive real numbers. And so this can't be a counterexample because you failed the idea of being a positive real number. So you would not select it. So anyway, not true. All right. On number 16, you're going to be asked, state whether it's possible for a deductive argument to be valid and sound. If so, make a simple 3 proposition argument that demonstrates your conclusion. And you're given, is it possible to have a deductive argument that is valid and sound? Yes. And they give you 4 choices. 3 of them are deductive arguments. Only one of them actually works. One choice is no, it's not possible, so you wouldn't pick that one. But you're looking for the one out of the 3 that is both valid and sound. So the issue is you want to find valid and sound. Again, only one of the 3 would meet both of those requirements. 16 is the same thing, or 17 is the same thing. 18 deals with inductive. 19, back to looking at deductive arguments using Venn diagrams to test for validity, and then talk about soundness. 20 does the same thing. 21 does the same thing. And 22. So that rounds it out. All right. I'm going to go ahead right now. So make sure. And it has happened from time to time. That's why I always try to do this right when I say I'm going to take care of this right now, where I have not assigned something. Now, by the end of next week, my goal is to have everything assigned out, at least a good bit in advance. But I need to set and go through some homework to make sure. And the reason I haven't put everything up yet, incidentally, is simply because once one student, by post an assignment, one student opens it up, doesn't even necessarily have to go in and work a problem, but once a student opens it up, I can no longer go in and edit. So I just, because I haven't actually taught this class in a while, I want to make sure I go through each and every assignment, and it's, all the problems are really good, and so on and so forth. And so by next week, I will have gone through a good bit of it, and we'll be able to assign a good bit more. So let me today is the 16th. So what I'm going to do is I'm going to put I put the due date at the 20th, which is Sunday. So that's just the day before the class. So again, remember, you can work past any due date. So even if you do not on Monday have it completely finished, not a big deal. But I now have assigned 1D. There will also be a quiz, and then I don't know, maybe about 6 problems. So our first quiz, which will go over 1C and 1D, and I'll put the due date for it also on Sunday. Now I need everybody, and I'm going to put an email out to this effect for the students who have not gotten into the class yet or haven't attended yet. Hopefully they will by next week. But this is very important information. On Monday, this should be the only time this happens, and I apologize for it. But my wife works in healthcare. She actually works in the OR on the heart team and open heart team. And she's on call a lot. And we never know when she's going to be able to get a few days off. Well, she got a few days off this weekend. And again, we're both avid outdoors folks, and we like to hit trails. And she actually has Monday off as well. And I was able to set it up to go down to Tennessee and down in the Smoky Mountains. We're coming back on Monday. Ergo, I'm not going to be able to have class on Monday. So what I'm going to do before I leave is do a Zoom session kind of solo, go over the material that I would have gone over in class on Monday, and then put that and send a link so that you can view it you can wait till Monday and view it then and work on the problems. And then we will have live class on Wednesday. I was also going to just go ahead and set up a Q&A on Tuesday, and I would just set it up for 11 o'clock. It's not mandatory, but since I won't have live class on Monday, give anybody an opportunity who wants to ask questions on homework on Tuesday, have that opportunity. And again, I will put a video together prior to leaving for Tennessee. Now, where I am, we're not going to rough it. We're not going to go out and do rough camping. So where I'm at has Wi-Fi. And so in the evening, if you shoot me an email, I will be able to respond once I get back to, basically we're staying in Gatlinburg. So, but I will have Wi-Fi, and I will check my email nightly. So is everybody clear on that? No class Monday. I will put a video up and make an assignment, and then we will have class on Wednesday, live class. And I don't, again, anticipate this happening again. But thank you. It was again, it's just tough for her to get days off like that. And so I told her we would. Yes. So I will, and again, I'll send the email to this effect, but I will plan to have a Q&A on Tuesday. And that's hilarious. On that last, somebody just messaged in, watch out for the bears. There is a heavy black bear population in that area. And I have come across, not in, because I've never hiked Tennessee. Basically, there's not a part of West Virginia I have not hiked in, and also trail run. I have last summer in Canaan Valley, I was hiking up the Canaan Valley ski area, and had a big old black bear come across the trail, and it's always, more than likely bears don't pay any mind to you, just don't agitate them. And he didn't. He never paid. It was me and I have a golden doodle trail dog, and I was like, "Hey, I tell you what, let's just turn around and head back the other direction. There's another way up to the top, and let that bear be." So, but my wife has never seen a bear live, or out, and she really wants to. So, scared to death of snakes, but yeah, she wants to see a bear. So we'll see if it works out for us. All right, so it is 12:16. The 120E doesn't start until 1 technically. So what I'm going to, if anybody has any homework questions, stick around, and if not, go ahead and take off. If you have, if you are in the 120E, we all kind of just take off right here. I'll be back at 1 o'clock. So if everybody jumps out, and so if you're supposed to be in the 120E, you should be able to leave the session, but come back in via the link. So that's where I've got my fingers crossed this will work out okay. If it does not, I will send out an emergency new link is what my plan is. So, are we good?
Thank you.
Thank you, and we'll see you if not next week on Wednesday, and if you're in 120E, I'll see you here in just a little bit.
Thank you very much.
Thank you, sir.